Today, we design a personal assistant chatbot like ChatGPT. Clarify requirements, languages, task range, non-text inputs, follow-ups, personalization. Frame as ML task. Input is a user prompt. Output is a coherent response. Use a decoder-only transformer for text generation, data preparation, extract, filter, and clean content. Remove inappropriate info, tokenize with BPE. Model development, architecture, decoder-only transformer, embeddings plus positional encoding, absolute, relative, or rope, transformer blocks, prediction head. Training, pretraining, broad language understanding, SFT, supervised fine-tuning on high quality, prompt response. Data, RLHF, human feedback optimizes helpfulness, safety, and preferences. Sampling for responses, deterministic, greedy, beam search, may repeat, stochastic, multinomial, top K, top P, adjust temperature and repetition penalty for natural diverse outputs, evaluation, offline, perplexity, task-specific benchmarks, safety, online, user feedback, engagement, conversion, leaderboards, system design, training, pipeline pre-training, SFT, RLHF inference, pipeline, safety filter, prompt enhancer, response generator, top P sampling, safety evaluator, rejection generator, session management for multi-turn conversations. This design ensures the chatbot is knowledgeable, safe, engaging, and context-aware for personal assistant use. The problem is to design a personal assistant chatbot like ChatGPT. What languages should we support? What's the range of tasks? How about non-text input? How about follow-up questions? Should the chatbot personalize interactions with users? In designing our chatbot, the first step is to clearly define the problem in machine learning terms. Our input is the text prompt provided by the user. This could be anything from a direct question, like, "What's the weather today?" to an open-ended request such as, "Tell me a story about space travel." The output is a relevant and coherent response that addresses the user's intent while maintaining the desired tone and style for our application. From a machine learning perspective, this maps neatly to a text generation task, where the system must produce a sequence of tokens in natural language based on the given context. For this, we're choosing a decoder-only transformer architecture, similar to GPT-style models. This design focuses exclusively on predicting the next token given the previous tokens, which aligns perfectly with conversational generation. During training, the model learns to capture context from the user's prompt and past conversation history, enabling it to generate responses that are not just grammatically correct, but also semantically relevant. The decoder's auto-regressive nature ensures that each generated token depends on all prior tokens, allowing nuanced and contextually rich outputs. Ultimately, framing the chatbot in this way allows us to treat it as a sequence-to-sequence prediction problem, but without a separate encoder, making it streamlined, efficient, and well-suited for dialogue applications. Before training a chatbot, we need to ensure that the data it learns from is both high quality and safe. This process starts with content extraction and parsing, where we pull raw text from various sources, such as websites, documents, or APIs, and transform it into a structured format that our model can consume. Next, we apply URL and domain filtering to exclude undesirable sources, such as spammy sites, untrustworthy domains, or content irrelevant to our chatbot's domain. Alongside this, language identification ensures that we keep only text in our target language or multilingual set, reducing noise in training. Quality filtering is a crucial step to maintain the chatbot's usefulness and reputation. We remove inappropriate content, such as hate speech, adult material, or toxic language, and anonymize sensitive information like names, emails, or phone numbers to protect privacy. We also discard low-quality data, such as text with excessive typos, garbled formatting, or meaningless filler. Finally, the cleaned text is tokenized, typically using byte pair encoding BPE, which breaks the text into subword units. This allows the model to handle rare words and new terms more effectively, and ensures that the model's vocabulary is compact yet expressive. By the end of this pipeline, we have a high-quality, privacy-safe, and well-structured dataset that sets a strong foundation for training a reliable and ethical chatbot. In designing our chatbot's model architecture, we use a decoder-only transformer, which is particularly well-suited for generative tasks. This architecture takes in a sequence of tokens, our text prompt from the user, and predicts the next token step by step until the full response is generated. The process begins with a text embedding layer, which maps each token into a dense vector representation that captures semantic meaning. These embeddings then pass through a stack of transformer blocks, each consisting of self-attention and feed-forward layers, enabling the model to capture both local and long-range dependencies in the conversation. At the end, a prediction head, typically a linear layer with a softmax, produces the probability distribution over the vocabulary for the next token. A key component here is positional encoding, which allows the model to understand word order and relationships across the context window. Absolute positional encoding assigns each token a unique position vector, either through fixed sinusoidal patterns or learnable parameters. This is the original approach used in the transformer paper. Relative positional encoding instead focuses on the distance between tokens, which is more flexible for varying length inputs and can better capture context in dialogue. Rotary positional encoding, ROPE, applies a rotation matrix to embeddings, smoothly integrating positional information into the attention mechanism and improving extrapolation to longer sequences. These design choices, especially in how positional information is handled, directly influence the chatbot's ability to maintain coherent, contextually relevant conversations over long turns. Our chatbot model training process involves 3 major stages: pre-training, supervised fine-tuning, SFT, and reinforcement learning from human feedback, RLHF. Each stage progressively shapes the model from a general language learner into a helpful, human-aligned conversational agent. First, pre-training goal. Create a base model with a broad understanding of language, grammar, facts, and reasoning patterns. Data. We use a large, diverse corpus collected from books, websites, forums, Wikipedia, news, and other public datasets, potentially trillions of tokens. ML. Objective. Standard next token prediction. The model learns to predict the next word, or subword token, given previous context. Loss function, cross-entropy loss, which penalizes incorrect token predictions. Outcome. The model becomes a general-purpose language model. It can write, summarize, and answer questions, but is not yet specialized for conversations or helpfulness. Second, supervised fine-tuning, SFT. Goal. Adapt the pre-trained model into a conversation-ready assistant. Data. High quality, curated, prompt, response, pairs. These are often written by human annotators to demonstrate ideal behavior, e.g., polite tone, safe content, structured answers. ML. Objective. Still next token prediction, but now the data is targeted toward instruction following and conversational flow. Loss function, cross-entropy. Loss again, but with a much smaller, cleaner dataset to reinforce desired patterns. Outcome. The model is now better at following instructions and maintaining a natural conversation, but it may still produce plausible, yet unhelpful or biased outputs. 3. Reinforcement. Learning from human feedback. RLHF. Goal. Make the model's outputs aligned with human preferences for helpfulness, harmlessness, and truthfulness. Step A. Reward model training. We collect prompts, generate multiple candidate responses from the SFT model, and have human annotators rank them from best to worst. From these rankings, we create preference pairs, winning versus losing responses. The reward model learns to predict a helpfulness score for any prompt response pair. Objective. Maximize the score gap between the winning and losing responses. Loss. Function. Margin ranking loss. Step B. Policy optimization. Using the reward model, we optimize the SFT model's behavior via reinforcement learning algorithms such as proximal policy optimization, PPO, or direct policy optimization, DPO. We repeatedly generate responses, score them, and update weights to maximize expected reward while staying close to the SFT model to avoid drifting into nonsense. Data here can range from tens of thousands to millions of annotated prompts. Outcome. The final chatbot model balances plausibility and usefulness, prioritizing responses humans actually prefer. Closing. Summary. Pre-training teaches language. SFT teaches instruction following. RLHF teaches helpfulness according to human judgment. Together, these stages transform a raw language model into a polished, safe, and engaging chatbot. When we reach the sampling stage, the model already has a probability distribution over possible next tokens. The challenge is deciding how to pick from that distribution so our chatbot produces coherent, helpful, and non-repetitive responses. We can divide approaches into deterministic and stochastic methods. Deterministic methods. Greedy search simply picks the token with the highest probability every time. While fast and straightforward, it often causes the chatbot to loop or produce bland, repetitive text. Beam search tries to look ahead at multiple possible sequences before deciding, which can improve coherence in certain tasks like translation. But for chatbots, it can be inefficient and still prone to repetition. Stochastic methods. These introduce controlled randomness, making them better suited for dialogue. Multinomial sampling draws tokens directly from the predicted probability distribution. It's highly diverse, but can feel too random. Top K sampling limits choices to the K most likely tokens, ensuring quality while retaining some variability. The downside is that K is fixed. It doesn't adapt to the situation. Top P, nucleus sampling, is more dynamic. Instead of a fixed number, it chooses the smallest set of tokens whose cumulative probability exceeds P, striking a balance between diversity and relevance. Advanced controls. Temperature adjusts the sharpness of the probability distribution. A low temperature less than 1 makes the model more deterministic. A high temperature greater than 1 makes it more random. Repetition penalty explicitly reduces the likelihood of repeating the same phrases, which helps avoid loops and makes responses feel more natural. In short, the sampling stage is about finding the sweet spot between creativity and control. The right combination of top P, temperature, and repetition penalties can make the chatbot sound engaging without drifting off topic. When designing a chatbot, evaluation ensures that the system is not only fluent, but also helpful, safe, and aligned with user needs. We can group evaluation into offline metrics and online metrics. Offline metrics are measured without live user interaction. The most traditional is perplexity, which measures how well the model predicts the next token in held-out data. Lower perplexity means better predictive accuracy, but it doesn't always correlate perfectly with user satisfaction. Task-specific evaluation uses specialized benchmarks. For example, common sense reasoning tests like Winograd schema, knowledge-based quizzes like Trivia QA, reading comprehension datasets like SQUAD, mathematical reasoning challenges like GSM-8K, and code generation benchmarks like Human EVAL. Composite benchmarks such as MMLU combine multiple domains for a holistic view. Safety evaluation tests, whether the chatbot avoids harmful outputs. This includes detecting and mitigating toxic or biased language, checking for fairness, maintaining truthfulness, preventing privacy leaks, and ensuring resilience against adversarial prompts. Human evaluation is still the gold standard. Domain experts or crowd workers rate responses for helpfulness, clarity, factuality, and tone. Online metrics come from real-world deployment. User feedback, explicit ratings, thumbs up, thumbs down, or comments, gives direct quality signals. User engagement measures how often and how long people interact, indicating usefulness and satisfaction. Conversion rate is relevant for commercial chatbots, tracking how effectively conversations lead to desired outcomes, e.g., purchases, signups. Online leaderboards like Chatbot Arena allow public head-to-head comparison against other models, offering community-driven evaluation. Overall, evaluation is iterative. Combining offline rigor with online insights ensures the chatbot continuously improves while staying safe and aligned. In designing a chatbot, we can think of the architecture as two major pipelines: the training pipeline and the inference pipeline, each serving a distinct purpose. 1. Training pipeline. We start with pre-training, where the model is trained on large-scale text data to learn general language patterns and knowledge. This gives the model its broad world knowledge and linguistic fluency. Next is supervised fine-tuning, SFT, where we train the model on curated datasets with high-quality instruction-response pairs, making it better at following human-like instructions. Finally, we apply reinforcement learning from human feedback, RLHF, which aligns the model's outputs with human preferences. Human evaluators rank responses, and the model learns to produce answers that are more helpful, safe, and contextually relevant. Second inference pipeline. When a user interacts with the chatbot, the process flows through several safeguards and optimizers. Safety filtering checks incoming queries for harmful or prohibited content, blocking unsafe requests early. Prompt enhancer improves the input, for example by rephrasing vague prompts into clearer, more informative queries, which helps the model respond more effectively. Response generator uses techniques like top P sampling to create coherent, high-quality responses while balancing creativity and accuracy. Response safety. Evaluator runs a final safety check on the model's output before showing it to the user, catching potentially harmful or biased content. Rejection response generator provides a polite, informative refusal if the input is unsafe or if the generated output fails the safety check. Session management ensures smooth conversation flow by keeping track of chat history, maintaining context, and enabling multi-turn dialogue. Overall, this architecture ensures the chatbot is knowledgeable, safe, responsive, and engaging, balancing technical sophistication with user trust.